All right, here we are back in sound. Okay, we were just talking about types of waves. An example would be if you take these two slinkies, and we can see the two types of waves demonstrated for us. In the first case, you have a slinky that has been stretched out, and then some of it gets close together, and you let it go. And as it goes across, it spreads out, close together, spreads out, close together, spreads out, close together. All right, and this type of wave is called a longitudinal wave, or you may hear it called a compressional wave, and I kind of prefer this name for it because the parts of the wave are being compressed together, spread apart, compressed together, spread apart. This is the type of wave that we would expect a sound wave to be. When you talk, your vocal cords vibrate, and when they do, they squeeze air molecules together and they spread out, spread together, and that's how the sound carries across someplace. That's why sound has to have air or some kind of medium, liquid, solid, something for it to travel through, because it has to be squished together, spread apart. Okay. Now the other type of wave, which is more like what we looked at earlier with the picture, is where it goes up and down, up and down, up and down. That's what we tend to think of as a sine wave or some type of wave like this. And this is going to be called a transverse. Okay. Now, the official definition is that this wave vibrates, okay, in the same direction. They go this and back and forth in the same direction that the wave is moving. The wave is moving this direction, and they squeeze together and spread apart in that direction, or the opposite, depending on how you want to look at it. Okay. On the other hand, a transverse wave is going this direction, but it is vibrating up and down, back and forth, up and down, and so it is perpendicular to the direction the wave is traveling. It's going this way, but it vibrates perpendicular to that. Now, in this case, this shows it up and down. It could be side to side, it could be from angle to angle, but the whole point is it could rotate 160 degrees, but it's basically going up and down perpendicular to the direction the wave is going. Okay, and so those are our two types of waves: transverse and compressional or longitudinal. All right. Now, when we look at sound wave, we said they are compressional waves or longitudinal. Okay, because they go the long way, they go the same way, it's vibrating. Okay, so if we do a tuning fork, or like I said, it could be the vocal cord in your body, it is squeezing atoms together, spreading apart, spreading close together, and spreading apart, and so forth. Okay, now this has the same parts of a wave that we talked about when we were talking about a transverse wave. The compressions are where it's close together, so each one of these is a compression. A compression would be like a crest, okay? Where they're spread apart is rarefaction. They're more spread out. Think about it, they're rarer. The molecules are rarer there, or spread out more, so it's a rarefaction. All right. The distance from one compression, try that again, from one compression to the next compression would be the wavelength. All right. That would be one wavelength, or from one rarefaction to one rarefaction. Okay. Now the amplitude is a little more difficult to show, but basically amplitude has to do with how closely together these are squished apart and how far apart these are spread apart. Okay. If you have a high amplitude, if they were really squeezed tight together, that would be a higher amplitude. And then also, if you're going to have a high amplitude, that means the in-between part, they would be spread really far apart. And then when you get to the compression again, they would all be tightly squeezed together. Okay, so we would say this one has a higher amplitude. It would be a louder sound, basically, than this one because they are squeezed together. Now, the frequency would have to do with how far the length of the wavelengths, okay? And since these are spaced about the same, they would have the same, this wave would have the same frequency as this wave because the wavelength is about the same, and therefore the frequency is probably going to be the same, okay, assuming that they're moving at the same speed, okay? So notice once again, regardless of the frequency, the speed of all sound waves are about the same, at least if they're going through the same medium, air, water, or solid. Okay? Now, the frequency, though, has to do with what we call pitch. We talk about high-pitched sounds way up there, and we have low-pitched sounds, which are way down here. Okay? And basically, pitch is related to frequency. Okay? So with pitch, if a sound wave has a high frequency, then it's going to have a high pitch, or a high pitched sound. Okay? If it has a low frequency, be a long wavelength, then it's going to be a low pitched sound. And so when we change our voice to go high pitched to low pitched, or singing, you're going to higher pitches and lower pitches. Basically what you're doing is you're changing the frequency of the sound wave coming off of your vocal cords. Now when we measure the frequency of sound, we're going to use hertz, just like we talked about before, for any vibration. Okay, and humans can hear anywhere from about 20 hertz all the way up to about 20,000 hertz. Okay, so you can hear up about 20,000 hertz. All right, and so between those, that's what the sound that we can hear. The lowest pitch is about 20, the highest is about 20,000. Now, for example, I probably can't hear 20,000 hertz. I have lost some of my high frequency. Part of that's just due to age. As people get older, they can't hear those high frequencies. My students would like to get little apps that will play frequency sounds, and so they would play really high ones. Everybody else was like, "Ooh, stop it! It hurts my ears," and I wouldn't hear it. Okay, but that's okay. That's just kind of a natural thing as you get older. All right. Now, if it's lower than 20 hertz, less than 20 hertz, okay, then that sound is called infrasonic. Infra kind of means less than, so infrasonic is too low of a frequency for us to hear. Okay, whales apparently make a lot of sounds that are infrasonic. We just cannot hear them. On the other hand, a dog whistle is the other end of the spectrum. Those are sounds greater than 20,000 hertz. Okay, and these are called ultra, which more than or above or beyond. Okay, so ultrasonic waves. Not to be confused with supersonic. Supersonic we'll talk about later. But ultrasonic means it's at too high a frequency for us to hear it. And so a dog whistle that we cannot hear would be above 20,000 hertz. But dogs can hear that range, so they would still continue to hear it. And this is probably why a lot of large sirens and a lot of times will cause dogs to either cringe or just go crazy barking or because they're hearing probably some frequencies that we do not hear, that those things are still producing. Right? Now, if we talk about the speed of sound, it depends on what it is going through. If the sound is going through air, or if it's going through water, or if it's going through a solid. In fact, it even depends on whether, for example, in air, is it humid air or is it dry air? It's still going pretty fast either way, but it does change it. Okay, so for example, if you have dry air, just no humidity in it at all whatsoever, we would say that sound would travel at 330 meters per second. Right. Knowing that a meter is about a yard, actually a little bit longer, so this is about 3.5 football fields per second, 300, probably around 50-ish yards. Okay, so about 3.5 football fields per second. That's pretty doggone fast for as far as we're concerned. Okay, now it's not as fast as light, which we'll talk about later, but it is a fairly fast sound. Now in moist air, which most air has at least some humidity in it, so we usually, that's why we said, I think earlier that we said the speed of sound is 340 meters per second, because most of the time there's going to be some humidity, and that's a pretty good average that we usually use if we're going to talk about it. Now, just for the record, if you wanted to make this in miles per hour, you basically multiply it by 2 times 2. Okay, and so it's going to be over 660, 680, around 700 miles per hour. So very, very fast. Okay. compared to most movements that we're used to. Okay, now basically, since it is vibrating, substances that have atoms closer together are going to be able to pass those vibrations on better than those that are far apart. So basically, you're going to have the fastest movement in solids, because in a solid, your atoms are right next to each other. If one vibrates, it quickly passes that on to the next one. Okay, so it will pass it on faster. Okay, in fact, if you go in steel, a piece of steel, the sound will travel about 15 times faster than it will in air. Okay, if you go to water, which is where they can kind of slide around each other and move around, then it's going to be about 4 times faster than air. And of course, air would do it in 1x, or 1 time as fast as it can go in air, because it's air. All right, so basically, air is going to be the slowest. Now, someone said, but that's what we hear it in. Now, notice we're talking about fastest. Okay, and the problem is we can really only hear things in air, because even if we're underwater, it travels through the water to get to our ear, but then it has to go from water to air into our ear, into our eardrum, unless we get our ears completely full of water. Okay, but basically it will travel faster. Now, it may not be as easy to see or hear or recognizable for us, but that's partly because we have air in our ears, and so it's hard for it to go straight through the water and actually hit our ear. There are several things that can happen when sound hits an object, okay, when it hits a surface. Okay, it can, one, be transmitted, which means that it just goes right through the surface. All right. Well, for example, if this speaker or a speaker at the top of the room, someone sitting in here, some of the sound may continue going through the wall into the room next to it, particularly if it's not a very thick wall, or it hasn't been soundproof, or doesn't have acoustical tiles or anything, or whatever. Ours had cinder blocks, so they pretty well block sounds, but it could transmit the sound. It could continue to pass on through, and so when you hear that, usually it's more muffled and quiet, because most of the waves aren't passing through, but some of them can be transmitted or pass through the surface. Some of the energy can be absorbed by this. If we had a soundproof room, usually there's a bunch of air spaces and material with a lot of air spaces, like I'll say styrofoam, but something like that, where there's a lot of air space and stuff, and it absorbs most of the sound. So before it gets through the wall, most of it has been absorbed into the wall. Okay, and sound energy is just like any other kind of energy. It can be absorbed or changed to a different kind, heat or something like that. Okay, so it can be absorbed by the wall, all right, or it can be reflected or bounce off, which is what we're showing here. For most auditoriums or classrooms, we would want it to reflect, because we want all the sound to get to the people. Okay, and so we would want to reflect. And reflect just means it's going to bounce off, just like light hits a mirror and bounces off and comes to our eyes, so we see a reflection in the mirror. Same way happens with sound. Okay, basically, to make it the best surfaces, if we want it to be reflected, the more rigid it is, okay, stiff, hard surfaces, vibrations bounce off. Just like if we have a soft floor, you don't bounce off it very good. It's hard to dribble a basketball on a carpet, but if you have a hard floor, then it's going to bounce better. Same kind of thing here for reflection. All right. Also, the more rigid it is, also the smoother it is. Okay, more smooth, I guess. But if it's more rigid, if it's smoother, then it's going to bounce off. Basically, if you have a rough surface, it may bounce off, but it's going to bounce off in different directions, and so it's going to, some of those waves will interfere with each other and not all be coming in the same direction. So we want them to smoother, give us a better. If it's rougher or more irregular, the less it's reflected, or at least it's less reflected in a way that it brings the sound to the hearer. It's going to be lose a lot of its quality to it, because it's going to bounce off in all directions. Now, if we hear an echo, a reflection, we call it an echo. All right, so that's really all an echo is. If you yell into a canyon, some of those waves hit the walls on the other side and bounce back to you, and that is an echo. All right. For our next one, we'll talk a little bit about reflecting of sound, and we'll move on to our next topic.